Weight is the enemy of automotive design, yet complex comfort features require more connectivity than ever before. The secret to vehicle efficiency goes beyond engine performance. It's in the connectivity of the different vehicle systems. Mulungi Steven is my name, and I'm the head technician at Nana Auto Diagnostics. And I want to welcome you to part 3 of the 7-part series on automotive communication networks. Today, we are diving deep into the world of LIN communication protocol. We shall understand how a single wire is able to control systems such as windows, doors, wipers, and other systems without breaking a sweat. Let's start by defining the LIN Bus communication protocol. Now, LIN stands for Local Interconnect Network and is a low-cost single-wire serial communication protocol used primarily in automotive networks. It is designed to handle simple, non-safety critical vehicle functions that are related to body and comfort, such as window regulators, seat adjustments, mirror controls, and others, where the complexity and speed of the CAN bus is unnecessary. The single wire bus connects a commander ECU and all responder ECUs. The commander ECU is known as the master, and the responder ECU is known as the slave. And the voltages are driven to 0 volts from a recessive 12 volts for binary signaling. And we shall explain that in detail later on. According to this master-slave architecture, the commander ECU, we can call it the master ECU, can connect up to 15 slaves or slave nodes on any given network. For instance, the body control module, sometimes known as the BCM, can control the central lock, can control wipers and washers, can control windows and other body and comfort related systems. Now, in this case, the BCM acts as our master, and the other modules will act as the slaves. So the maximum number of nodes any commander ECU in the LIN network can accommodate is 15. There are a few things that I would like to put straight before we continue with our discussion. And whenever we are carrying out diagnosis on the LIN bus, it's important to know that this type of communication is only used for module-to-module communication. So we cannot access this network on the DLC or the OBD2 port. It's only the J1850 and the K-line and the CAN, which can be used for the scan tool to module communication. LIN is only used for module-to-module communication. I've already covered the J1850 communication protocol and the K-line in the previous videos, and I will tag the links in the description below. For CAN, we shall look at that in our next video. So whenever you are going to diagnose any issue regarding LIN, just know it will be a wastage of time for you to start checking the DLC because you will not find it there. you have to go to the exact module where the fault is happening and you start your diagnosis from there. Next, let's look at the applications that employ the LIN communication network. And as we said, this communication protocol is usually used in body and comfort related functions on a vehicle. And these applications include seat adjustment motors, mirror actuators and window regulators, automotive climate control dampers, and HVAC sensor data transmission. Now HVAC stands for heating, ventilation, and air conditioning. We also have interior ambient lighting control systems, battery monitoring and management systems. We also have electric sunroof position tracking, smart windshield wiper speed, adaptive lights, intelligent fuel pump modules, and many others. Next, we are going to look at the LIN Bus message frame. In this video, we are going to be talking about the LIN Bus message frame, and we are going to go in depth to understand what happens when the master or the commander is sending the message and what that message constitutes. And we shall also look at the response from the slave. So let's dive right into it. If we have our master, which is sometimes known as the commander, trying to send a message to our slave. Now the slave is sometimes known as the responder. The message that is sent by the master is known as the header. And this is made up of 3 sections, which include the break field, the sync field, and also the protected identifier field. Once this message has been sent to the slave will have to respond back to the master, and that message is known as the response. And this contains mainly 2 parts, which is the data and also the checksum. Next, we are going to be looking at the header and the response. We see what is contained in each field and the role that is played by the different fields in those messages. At this point, we have already established that the message sent by the commander or the master is known as the message header and is made up of 3 fields, which is the break field, the sync field, and the protected identifier field. And before we go ahead to describe the role played by each field, we need to understand that whenever the bus is not transmitting any data, it idles at 12 volts. What do I mean? Whenever we don't have any transmission on the bus, it will be at 12 volts, usually battery voltage. Whenever we attempt to have some bit of communication, this voltage will be pulled to about 0, votes. So let's go ahead and explain the various fields that are found in the message header. So here we are talking about the message header. And remember, this is the message that is sent by the commander ECU to the slave or the responder ECU. So we shall begin our discussion with the break field. The break field acts as a wake-up signal to all the nodes or slave nodes on the LIN bus. Whenever the commander ECU or the master ECU broadcasts this field, it is alerting the slave nodes or the slave ECUs to be aware that it has begun its transmission, and it consists of a minimum of 13 0 bits and is always followed by a delimiter, which is bit 1. And this is how it would appear. So the 12 votes are going to be pulled down to nearly 0 votes, and this will go on for a bit period of 13 zeros. So we have 13 zeros, and this will be followed by a delimiter, which is of 1 bit, and it's always a logic 1. So this, from here to there, this is what we know as the break field. So this signals the start of transmission. Whenever the 12 votes are pulled to nearly 0 votes for a bit period of 13 zeros, and then followed by a delimiter, which is defined by a logic 1, this signals the start of communication on the LIN bus. And this will be followed by the sync field. So what happens is the master must send this field in order to synchronize its communication with the slave nodes. So this sync field, its main job is to synchronize communication between the master and the slave nodes. And this is made up of 8 bits, which are sandwiched between the start bit and the stop bit. And these 8 bits usually 0, 1, 0, 1, 0, 1, and 0, 1. Now this sync field will always follow the break field, and in total it will be having 10 bits. Now the other 2 bits will always come, 1 bit will always come before, which is known as the start bit, and the other bit will come after, which is known as the stop bit. So we are going to continue with our transition. So here, now we are done with the break field, so we are moving on to the sync field. And this is what we call the start bit. So this is the start bit here. Now after the start bit, we shall move on to our 8 bits. So that is 1, 2, 3, 4, 5, 6, 7, 8. Then we move on to the stop bit. So this bit 1, 2, 3, 4, 5, 6, 7, and 8. So these are the 8 bits I'm talking about here. And then this is known as the stop bit. So starting from here all the way to that part there, this will be common to all LIN networks in automotive. So this is standard. You always find it on any LIN network. Whether you probe a control module on a window or on a wiper, as long as it is using LIN, you always find this format. Now that's why I'm taking my time to explain this, because I want you to first understand these networks and the way they operate, such that when we move on to our practical sessions, it will be easier for you to understand them. And next, we are going to move on to our protected identifier. Now the protected identifier is also made up of 8 bits. It's made up of 6 data bits and 2 parity bits. So from the sync field, now we move on to our protected identifier field. Now this field will vary depending on the data that you'll be transmitting. Now within this field, it will contain the actual data that the master is transmitting to the nodes or the slave nodes. It will contain the purpose of that data and which node is supposed to receive that data. And for the 2 parity bits, those ones are used for error detection. Now, as you're transmitting this data, remember it's a single wire network. It is susceptible to electrical noise. So what happens whenever these 2 parity bits not match when that data is received by the nodes, that data will be rejected because it has been received in error. So the main function of the 2 parity bits is to ensure that we have data integrity as it is being transmitted on the bus. So next, let's look at the message frame that is sent by the slave node after receiving this data. Let's first look at this waveform and see how it appears on an actual LIN network. As you can see, the network idles at 12 volts, and when the master initiates communication, it does so by sending the break field, which acts as a wake-up call to all nodes on that network, and then that is followed by the sync field, which synchronizes the communication between the master and the slaves, and that is followed by the actual data that is sent by the master, specifying the purpose and the node that is supposed to execute that data. Now you can see the line goes back to 12 volts because we do not have response from the slave. Now by just looking at the waveform, I can tell that the master is sending communication on the bus, but the slave is not responding. So let's look at the message that is sent by the slave after it has received communication from the master. When the slave receives information from the master, it may take one of these three actions. One, it may just listen to that message. Two, it may publish or respond to that message. And three, it may do nothing. So let's look at the response from the slave when it receives data from the master. So we're looking at the response from the slave. And as we said earlier, this message contains two fields, which is the data field and the checksum. Now the data field contains the actual data that is being sent by the slave to the master. And the checksum, this is used to detect errors in any given data. Now you'll be able to appreciate these concepts and more when we move on to our practical sessions, where we shall probe these LIN networks and observe their behavior on the scope. And we shall subject the network to various faults such as short to ground, short to power, open circuits, and we shall be able to observe the behavior of the network in case one of the slave is shorted to ground or shorted to power, or even when that slave is unplugged. So if you have not yet subscribed to this channel, please subscribe, share, like, and turn on that notification bell so that you'll be updated every time we upload a new video. Thank you for joining me, and in our next video we shall be looking at the CAN bus, which is the controller area network.